Policy gradient methods. Policy gradient methods are a class of reinforcement learning algorithms that learn a policy directly by optimizing the parameters of a policy network. Instead of learning Q values like Q learning or DQN, policy gradient methods focus on finding the optimal action selection strategy that maximizes cumulative rewards. A popular approach is the reinforce algorithm, where actions are sampled for a policy distribution and the policy is updated using gradients based on rewards. Let's go ahead and look at line by line implementation of policy gradients methods. So I'm going to start with an empty file. I called it policy gradient methods.py. Let's go ahead and import our NumPy, which provides support for arrays and numerical computations. Then we'll get TensorFlow STF. This is used for defining and training the neural network, which is also from TensorFlow Keras import layers that will be used for that. And I'm going to import gem, which provides the environment interface here for the cart pole v1 environment. So let's go ahead and set up the environment. First, I'm going to say environment is gem.make cart pole v1, state shape equal to environment observation shape 0, and this kind of gets the number of state features, example position or velocity, and the number of actions equal to env.actionspace.n. This defines the number of possible actions left or right in the cart pole environment. Let's go and define the parameters. Learning rate equal to 0.01. This sets the step size for the optimizer to update the network weights. Gamma I'm going to set 0.99. This sets the discount factor, determining how much future rewards are considered. Next, building the policy. So for policy network, I'm going to say define build policy model, and here I am going to say model equal to tf.keras.sequential. Now this function defines this is a function that defines how to create the policy network. Now tf.keras.sequential, what it does is it's a sequential model where each layer feeds into the next. So let's go ahead and create these different layers here. So the first one is layers.dense 24 activation ReLU is the first hidden layer with 24 neurons and ReLU activation. So here is the entire one. The second one is the second hidden layer, which also with ReLU, and the third one is the output layer with number of actions output for action probabilities and softmax activation to provide a probability distribution over actions. Now let's go ahead and say model.compile. We pass these parameters. This compiles the model with Adam optimizer. As you can see, tf.keras optimizer Adam is what we're using, and passing learning rate to it. Next, I'm going to return this particular model. So next is to call that build policy model. So I'm going to call that function from the policy model variable, and this will call the model to create an instance of policy model that will be used to predict action probabilities. So next step is to create the action selection function. So here I'm going to create a choose action and pass state as the variable, state equal to np array. What this does is this reshapes state into a 2D array with shape of 1, state shape for model input compatibility. Now I'm going to say probability says policy.model predict state. This uses the policy model to predict the probability distribution over actions. And then finally np.random, this is what I'm going to return, chooses an action based on the predicted probabilities. That's why I'm passing the number of actions and p equal to probabilities at 0. So this function kind of chooses an action based on the policy network's output. Next, let's go ahead and do the discounted reward calculation. For that, I'm going to say discount rewards. Here, I'm going to pass the rewards as the input as the parameter. Discount equal to np zeros like rewards. What this does is it initializes an array to store discounted rewards. Then cumulative, I'm going to set the cumulative equal to 0 and then loop through I in reversed range length of rewards, which iterates backward over the rewards, and set the cumulative equal to cumulative times gamma plus rewards of I, which updates the cumulative reward with discounting. Now next I'm going to say discounted I equal to cumulative. This stores the discounted reward, and then returns the discounted minus np dot mean discounted, which normalizes the discounted reward by subtracting the mean to stabilize the training. So let's go ahead and work on the training function. So first, train on episode. This function trains the model on data from a single episode. So I say discounted rewards equal to discounted rewards. This calculates the discounted rewards for the episode. Now with tf dot gradient tape as tape, this starts recording operations for automatic differentiation. I'm going to say action prob equal to policy model tf dot converted to tensor states df d type equal to tf dot float 32 training equal to true. What this does is this will calculate action probabilities for each state in states. Next, I'm going to say action indices equal to tf dot stack tf range length of actions axis equal to 1. This prepares indices. This will prepare the indices to select the probability of the action taken. Next step is select action probabilities. This will extract the action probabilities for the chosen actions. So right here, we're passing the action props and action indices. And finally, loss equal to minus tf reduce mean tf dot math log selected action props times discounted rewards. This calculates the policy gradient loss using the negative log probability of selected action weighted by discounted rewards. Next, let's go ahead, get the gradients equal to tape dot gradient, pass the loss and policy model dot training variables. This computes gradients of the loss with respect to the model's parameters. And next, we're going to say policy underscore model optimizer apply gradient. This updates the model's parameters using the computed gradients right here. So next, let's go ahead and run the main training loop. I'm going to set the number of episodes as last time to 1000, and for each episode in this particular episodes, I'm going to say state equal state comma underscore environment reset. This what this does is this resets the environment to start a new episode and handles compatibility with the new gym version where reset returns a tuple. And then episode states, episode actions, episode rewards, everything is set to empty. Initializes this list to store states, actions, and rewards for each episode. So once I have that ready, I'm going to run a while loop or episode loop where action equal to choose action state. This selects an action using the policy. Next state equal reward done truncated equal to environment dot step action. This takes the action in the environment and gets the resulting state, reward, and done flags. Then I'm going to get done equal to done or truncated, which again as last time ends the episode if either done or truncated is true. Then I'm going to say episode.state append state, episode.action append action, episode rewards append rewards. These stores the state, chosen action, and received rewards in their respective list for each step. Next, I'm going to go through the next step and say state equal to next state, which updates state to the next for the next step in the iteration. I'm going to say if done, what I want to do if it's completed, when episode ends, I'm going to say episode state equal to npv stack, converts the episode states into a 2D numpy array, and then train on episodes. This trains the model on the data from this episode. As you can see, this takes that variables, and finally I'm print the logs here, logs the episode number and the total reward, and then break out of this loop. So this code trains a policy network using policy gradient reinforcement learning on the cardpole v1 environment, and each episode's discounted rewards are used to update the policy network, and actions are selected based on a probability distribution predicted by the network. Let's go ahead and run this. I'll save it first and say Python policy, run it. It's going to take some time because it's going to run through 1000 episodes. So, and currently I am at 7, 8, 9, 10. If you see here, shows the episode number. So I'm going to give it some time and then come back. It's going to take a way lot of time as compared to the last ones because it has to run through the 1000 episodes. So it took a little bit time, but finally we are at episode 1000 with a total reward of 500. It took forever to go through this, but if you want to try something, you can just reduce the number of episodes and then train this. If you had any questions or any problems while running this, let me know and I'll get back to you.